Today we'll be talking about a falling object and the conservation of energy. So let me draw out this little ledge for you. And we have our ball at the top. Assume that's sitting right on the floor. And this ball is going to be pushed off the ledge and falling all the way down. Now the height of this ledge is 10 meters. So someone might ask you, well, find me the velocity of this ball once it hits the ground at exactly 10 meters. I say, okay, well, what's its mass? Well, actually, you don't need to know the mass, which is very interesting. And I'll tell you why. So we have that potential energy is equal to mgh. You say, wait, well, there's mass in this equation. Well, don't worry. We're not there yet. Then we have kinetic energy, which is equal to half mv squared. Wait, mass showed up again. Really looks like we'll need mass. But, trust me, we don't. So, we're looking for velocity. We have the height. We have this little g, which we know is 9.81 meters per second squared. And we do not have these masses. So we have two unknowns and two knowns. But what's interesting is the mass in each equation will eventually cancel each other out, and I'll show you how that works. So in a falling object, I'm going to tell you guys that in this scenario, no energy is lost. Now this is a very important statement, and it needs to be remembered. Is if a ball falls, in reality, obviously there is energy lost in air friction and sound and all those other things that exist, but in our scenario, this is an idealistic fall, and no energy is lost. So all the energy is conserved. So we can say that PE, potential energy, is equal to the kinetic energy. You say, okay, well that's great. So potential energy is all conserved at the top. So we have all our potential energy at the top, and we have all the kinetic energy at the bottom, right the instant as it hits the ground. And then what's interesting is that the potential energy at the bottom is equal to 0. And the kinetic energy at the top is equal to 0. It's because at the top, it's not moving. So when an object's not moving, it has no kinetic energy. And at the bottom, it's fully moving, and it's not stopped at all, so there's no potential energy. So, yeah, we can just say that potential energy is equal to kinetic energy. So we say that mgh is equal to half mv squared. Now, this cancels out. So if we bring this m over, so we can do it the long way here and just say divide by m. M over m is 1, so on each side we'll just have 1. So our equation will end up looking like gh is equal to half v squared. Okay? Now you can rearrange this a little bit to solve for v, because we know these two. So we say 2gh is equal to v squared. We're just moving the half over. Then we can take the square root of both sides, and we say that v is equal to the square root of 2gh. Okay, and what is g? 9.81 meters per second squared. I should probably write that down just so that doesn't confuse anybody. We should always write down our units. And then h, which is 10 meters. And take the square root of all of that, and it ends up equaling 14 meters per second. And that is the velocity of this object the instant as it hits the floor, or right before, whatever you'd like to say.